Swayam Prabha. Digital India. Educated India.
Hello, welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT KANPUR. So we are in the final week of our course on Nonlinear Adaptive Control, and I really hope that you have learned sufficient material to be able to design algorithms that can drive autonomous systems such as what you see in the background. Now, as always, we are interested in all sorts of applications. Of course, what you see here are mostly aeromechanical systems in the background, which is due to my own interest in these. But of course, adaptive control designs are not restricted to these, and you can use it on power networks and biological networks and so on and so forth. Yeah. So I'm always open to hearing more about sort of applications that you folks are envisioning the use of adaptive control. So, what we are looking at in this week, in this final week, is the connections with learning. And we are now specifically looking at sort of a deep learning problem. But of course, here we are sort of different in the typical different from the typical learning sort of results, in the sense that we are not doing the learning offline and then implementing it later, but we are doing learning and control simultaneously. We can do this because essentially this is connected to parameter learning, which we already know very well from. So that's what we sort of apply. Yeah. The only difference, or which is of course a significant difference, is that now we have a very nonlinear regressor parameter form, which is not what we were used to until now. Right? We are always assuming linear parameterized rather nonlinear, and so we still have to see how we can deal with this kind of nonlinearity. About how my robotic arm dynamics looks, because this is the application that we are going to be looking at for the use of these neural nets. And we saw the basic Euler-Lagrange dynamics, what each term means, what is the joint on the world space coordinates, and we also constructed this error variable with respect to a desired arm trajectory, and we also defined this backstepping error type variable, which we have seen before, and we wrote the dynamics in terms of this backstepping error variable. And in this dynamics now we have this function f, which is called the nonlinear robot function, and this is the function, as you can imagine, we will approximate using our 3-layer neural network. Yeah. So this is where we were. I'm going to mark our lecture here. It's lecture 12.4. Right. So now if you look at how we want to design our controller, what we do is we put in an approximation or a estimation of f, and that's called f hat. So unlike what we've seen in adaptive control before, we are not just estimating parameters, but we are now estimating functions, and that's why we have the notation f hat. Okay, and then of course we have a kv times r, which is like a gain matrix, symmetric positive decimal gain matrix, times this backstepping error variable r. Right, so this is the control. Yeah, so it's called tau 0 because we design the control sort of assuming that there is no disturbance. Right, we cannot do anything to sort of really cancel the disturbance here, so we just design a control assuming there is none. And this is, you sort of try to cancel this guy with its estimate, just sort of getting motivated from the certainty equivalence type idea. And we leave this term as it is, right? Because honestly, this term is going to cancel out on its own. So we don't worry about this term. Great. Now, so as we mentioned, f hat is an estimate of f by some means which is not yet disclosed. So what happens to the closed loop system, right? So uh, so there is this notation error here. So the closed loop system is not Km but Vm, becomes this guy minus Kv plus Vm times R and plus an F tilde and this tau d. Right? And this is where you have sort of this F tilde, which is the function estimation error. So this is just a term zeta naught, which is combining these two. Yeah, nothing special about this. All right. So this is essentially like an error system. So I'm going to highlight this. And so this is sort of the error system. Um, and, and of course, it's driven by the function estimation error. Right? So this F tilde, of course, shows up here. So um, so this is sort of like, I mean, although the tau zero seems to have only one term, which is KVR. I mean, it has two terms, but one of them is to more or less counter the effect of the nonlinear robot function. And the other term is what is the like the stabilizing term that we usually inject. And this term, although it looks like just one term, it's in fact a proportional derivative type term because of the nature of R. Right? So I have a E dot term and an E term. Right? So this is important to remember, right? That it has both a proportional and a derivative type term. So a PD type controller. Very again something which is very standard in aeromechanical applications. Even for space stuff, PD type controllers are known and found to be stabilizing. Yeah. So in the remainder of the paper, the authors use this equation 14. Yeah. And we of course focus on tuning this neural network in a smart way so that you can get R to go to 0 because you want R to go to 0. All right, great. So why is it? I mean, once very quick aside, why is it sufficient for R to go to 0? I want to quickly point that out wherever R is defined. Okay, so sufficient for R to go to 0. Yeah, why? Because this means that E dot plus lambda E equal to some phi function. This goes to 0, which means E dot is equal to minus lambda E plus phi. Right? And what do I know about phi? Suppose if phi is also bounded, we can prove that phi is bounded, which means R is bounded. If let's see, I'll put it properly. If R is bounded, that is L infinity, and R of course goes to 0, implies phi is bounded and phi goes to 0, right? Which means that, and what do I know? I know that this is a stable system, right? Because lambda is positive definite symmetry. So this is a stable system with a bounded forcing. So you already proved this kind of a result when we did this Ortega construction a long time ago. That if this E dot plus lambda E type thing goes to 0, then E has to go to 0. Right? So this immediately implies that E comma E dot both go to 0 as T goes to infinity. Yeah, so it's enough for us to show that R goes to 0. Right? So that's what we aim to do. Right? This is essentially like an Ortega type construction idea, right? And even in the Ortega construction, we did the same thing, right? Great. So if you don't remember, again, I would ask you to go back and refer to the Ortega type. All right. So that's what it's mentioned here. Yeah. Right. So E exhibits stable behavior. In fact, E is less than R. I mean, even if you don't have, I mean, of course, we are talking about R going to 0. In this case, that may not happen. But even if R remains bounded, right, has some nice bound, or just by virtue of this equation that R is E dot plus lambda E, then it can be shown even without talking about things going to 0, because honestly speaking, in this article, we'll not be able to prove that uh, anything goes to 0%, but we only prove nice bounded performance. Right? Because after all, whenever we talk about using neural networks for functions, it's eventually an approximation of the function. So there's always some error. So obviously, if there is some error, you cannot expect, just like in case of the disturbance, you cannot expect to for things to converge to zero. Yeah. So the best you will do is get some kind of bounded performance. So just with the relationship between E and R, you can actually conclude that the 2 norm of E is bounded by the 2 norm of R. And similarly, the 2 norm of E dot is also bounded by the square of uh, norm R square, norm R. And so this is important to remember. Okay. Then we also have very standard properties of the robot model. So M is basically positive definite symmetric, and therefore it satisfies this kind of an inequality. Right? So you remember that whenever you have positive definite symmetric matrices, you have this kind of an inequality. Yeah. The second property is that VM is bounded. Yeah. And by some continuous function multiplied by norm. Right. This is again a property of the centripetal Coriolis term. Okay. And the third property, which is a very important property in the Lyapunov analysis, is that the matrix M dot minus twice VM is skew symmetric. Right. What does it mean? It means that any quadratic form, which is alpha transpose M dot minus 2VM alpha, is 0. Yeah. So the quadratic form corresponding to any skew symmetric matrix is always 0. And so that's what we have in property number 3. Of course, we assume that the disturbances are bounded. Right? So norm is missing here, but yeah, we assume that the disturbances are bounded. This property 5 we don't use yet. I mean, we don't talk about it. So we are, which is why there is a psi naught and R. Yeah, that's why you had the psi naught here. Sorry, the zeta naught here. Right. So if you remember, uh, the zeta naught that was sort of inserted here. Yeah, the purpose was to talk about passivity, but you remember that we said that we'll not discuss the passivity aspects of this article uh, in these series. Yeah, so as of now we skip it. If we need to, we'll talk about it later. Yeah, right. This is a property. Yeah, so this is not an assumption. So these are properties. Yeah, so it's not like we are assuming anything. So of course this property can also be proved. There's a nice reference that's given for this. All right. Excellent. Excellent. So now we know that we need only good behavior of the R variable, and we have the dynamics of R given by this equation 14 here. Yeah, which is also something nice. Now, if F tilde was 0 and tau D was 0, then this is well known to be a stable, asymptotically stable system. Yeah. So if both of these are 0, then you are in very good shape. No problem. Yeah. Now the issues happen when this is non-zero, and of course there is disturbance. So of course that also, if it's non-zero, then this is at least bounded. So you want some bounded performance. So what you need at the least is that you have some nice bound on this F tilde. So this is the least you want. So you want a good function approximator. So that is why you start talking about the neural network control. Yeah, that is where we start discussing the neural network control. Right. So uh, so that's what we say, that this nonlinear robot function, if you remember, 11. So this guy. Yeah, this whole thing, assume that it is given by a neural network, as in 3. Right? So it's essentially like the function fx is replaced by this kind of a weights thing. Right? I mean, you had it here. And you had it here. Yeah, suppose this function fx is approximated in this manner. where of course epsilon is small enough. And then you have these weights and offsets and so on, and this activation function. So it's like a approximated by a 3-layer neural network. Now, why can we do this? Because we, by this nice theorem 2.1, we have that, you can approximate almost any continuous function in this way. Yeah? And fx is, of course, continuous. Right? So, of course, we have this fact that this error is bounded by some constant epsilon n. Right? So, you always need bounds on the errors. Right? If you don't have bounds on the errors, then you can't get bounded performance. Yeah, even with your Lyapunov analysis. Right? So, of course, there is results which say that these ideal weights are not necessarily unique. Yeah. So, I mean, that's, one cannot expect, like, when in standard adaptive control problem, the value of the parameter is sort of fixed and known. For example, if you say the mass of your drone is unknown and you use an adaptive controller, so the mass is a fixed quantity, right? You know what the mass is. Well, you don't know what the mass is, for example, but you know that it is a fixed quantity. But in this case, that's not necessarily the case, because these are not masses and properties of the system, but these are more like weights to some kind of sigmoidal function, which is used to approximate uh, uh, actual nonlinear function. So therefore, the choices are not necessarily unique. Yeah? So we should keep this in mind. So of course, this, according to theorem 2.1, this mild approximation assumption always holds for continuous functions. Right? So, right. So anyway, so this is of course, this is of course the important part here. So then, of course, just for we define a new notation, which is this z equal to w00v. This is just to make our lives easy in terms of notation. Right now, before doing any actual neural network type of design, what we want to do is to look at a few different bounding assumptions and facts. Right? Some of them are assumptions, of course, and some of them are facts. That is to say that some of them are guaranteed to hold true and others have to be based on some assumptions. Right? So the first is an assumption. The facts are easy to prove given the assumptions. Yeah? Therefore, we start with the assumptions. The first assumption is that the weights are bounded. Okay, this is a very fair assumption. I mean, if the weights are not bounded, then possibly your function x is not bounded. Function fx is not bounded. Okay, so having bounded weights is a very reasonable assumption. Yeah, good. The next is that the desired trajectory is also bounded. Yeah, so desired trajectory is defined by QD, but here we talk not just about QD, but about all the derivatives, or at least two derivatives of QD also. Now, this is again no different from the assumption which we made in our previous adaptive control problems. We just said it in words. We said that you have a bounded trajectory with bounded derivatives. Yeah? So here we are making it a little bit more specific. We have taken QD and its two derivatives. Right? So it's again a very reasonable assumption. You don't want your system to be following trajectories which are too sharp or too jerky and so on. So therefore, you do assume that you have bounded reference with bounded derivatives. So this is again something very reasonable. The important thing here is, of course, that this is a known constant. So you know this value. And similarly here, also you know this constant. So the important thing is that you know these bounds. So, yeah. In case of trajectory, of course, this is not difficult, but in case of weights, knowing a bound is sort of the kind of thing we assumed when we talked about projection in adaptive control, right? So in this case, we are, posteriori assuming that there is a known bound on the weights that we are trying to learn. Then we come to the first fact, which says that for each time t, x is bounded in this way. Yeah. So x is bounded means it's not like a uniform bound or anything, but we know that x contains of consists of what? X is okay. Sorry. X consists of Q. Well, actually, I should probably point it out here. Yeah. So if you look at this, uh, I'm sorry, where did we define X? Yeah, right here. So the X is defined this way. And so X contains what? It contains QD and its two derivatives. So these we already know are bounded by the cap QD by our assumption. And then the error contains E and E dots. So these contain what? These contain again Q and QD dots. Q and QD and QD dots and Q dots. Right? And this is of course bounded by some R along with some QD. Right? So this is not difficult to see, right? Because that you can actually get this sort of a bound on X, yeah, like a linear bound with respect to a fine bound with respect to R, yeah, right. So now, we sort of want to talk about using some kind of Taylor series approximations so that we can in fact do deal with these non-linear regressor parameter form. Yeah. Remember, the linearity in the regressor parameter forms is what helped us design most of our adaptive controllers, right? Without that, we would be in quite a soup. Yeah. So, so this is what I mean. It is E for extending linear NN to non-linear NNs, right? And this requires use of Taylor series based results, right? So this is uh, what is important, right? I mean, eventually when we have non-linear regressor parameter forms and non-linear terms in the neural network, we still want to look at some linear versions, and we do it by uh, taking Taylor series approximations of these non-linear terms. Because without the linearity, it would be impossible to deal with the structure that comes about and different kind of non-linearities that come about, and it would be impossible to get any kind of stabilization results. Okay. So so we of course, as always, assume that V hat and W hat are estimates for the ideal weights, right? And we of course define the tilde versions for V, W, and Z, right? And of course, we also have the sort of error in the activation function values. This is defined using this notation as sigma applied on V transpose X and sigma applied on V hat transpose X. So this is again a notation, right? So what we want to do is to sort of expand this with some kind of linear terms, right? And that's the whole idea, right? We want to use the Taylor series, right? So Taylor series gives us some linear terms, right? This is standard when we linearize non-linear systems also. Okay, great. So, so what is the Taylor series expansion of say this V transpose X? We know that V can be written as V tilde plus V cap. So we take the V cap as the center sort of, and so we have sigma V cap transpose X. Yeah, and then you take the sort of you sort of take the derivative with respect to your V cap this V cap transpose X term. So you take the partial or the derivative with respect to X, right? And that is what is this sigma prime notation, right? And then you have multiply with the error term, which is this V tilde transpose X, right? And then you have all the second and the higher order terms here. Okay, I'm sorry. I think right. You have the higher order terms right here. All right, great. So of course this is defined. So this is defined as partial with respect to some sigma prime is defined as derivative with respect to some z evaluated at z hat and so on. And OZ square of course define higher order terms. And this is all well known, right? So of course there are some the authors point to some other reference where a different Taylor series was used, but that's okay, right? So now of course we the authors want to simplify notation, so they call this term as simply sigma hat prime. Why sigma hat prime? Because it's sigma prime evaluated with this hat term. Right? So that's the rationale for using this kind of a notation. And so what do we have? We have sigma tilde as sigma minus sigma cap. And so sigma, we use, this kind of an expansion here, right? So what do you have? So sigma cap also contains, sigma cap is essentially this guy, right? So whenever if I subtract these two, yeah, I just get this term, right? That is sigma prime. We had transpose. So let me fix this. We had transpose x, right? And this v tilde transpose x. So you get these two terms right here. Okay, and then you have a second order term. So this is of course simplified. We just call it sigma hat prime, and this is v tilde transpose x. Right? So this term is just to, I'll just mark it. So this term is just this whole guy. Yeah, it's just a shorthand. It's nothing other than that. Okay. So now there is also the requirement to put some kind of bounds on the higher order terms, and so the authors do that. So this kind of a bound is sort of used, and again, this is, I believe, transpose. Right? So this is like this kind of a bound. Right? It is. So let me see. I'm trying to see if this is any different from what we have. Different bounds are put on the. Okay. So this term is bounded with again this sigma tilde, because this looks like sigma tilde. Yeah. So essentially, this. Honestly speaking, this bound is essentially derived from this equation. Right? Because if I take this on one side, I simply have this subtracting this, and this is sigma tilde. This is essentially sigma tilde, and then you have this guy here. Yeah, so this is what you have. So this, if this guy is to be evaluated, then you take this to the other side. So you have sigma tilde, which is this minus this whole thing. This whole thing, right? Right. So now, in order to get some kind of a reasonable bound for this term, you use this expression 24, right? So you have a fact 4, which is that for sigmoid, RBF, and tan hyperbolic, so all the three activation functions that we looked at, you have this to be bounded in this way, right? And these are, of course, obtained using some kind of bounds on these guys, right? So this is somehow using that. So because you see that these bounds also contain the Frobenius norm of V tilde itself, right? So these bounds are obtained using this expression right here. Okay, so that's the whole idea. Okay. All right. So of course they also use the, not just the they also use the fact that sigma and its derivative are bounded by constants for the RBF, sigmoidal, and tan hyperbolic. So of course, the authors mentioned that for nets greater than 3, these kind of bounding and these kind of ideas and are not too difficult to extend either, and then it can be done. All right. Excellent. Great. So what did we look at in this session is that we had already seen the robot dynamics. So we saw a little bit more of, sort of how the control structure looks in today's session. We also saw how the nonlinear robot function looks, right? And we understood why r going to 0 is sufficient for our purposes. And finally, we once we understood that this f tilde, that is the function approximation error, is what we want to drive as close to 0 as possible. We understood that this is where the neural network comes in, right? So this neural network is used to approximate this function using this theorem that we looked at earlier. We know that uh, you know, we sort of know that this function approximation using neural networks will help us to get close to true value of f. Therefore, f tilde can be made to have like an epsilon n bound, right? And that's what we looked at how this neural network approximation will work, how we use the Taylor series to sort of linearize the terms in the neural network and bound the nonlinear terms. And this is what we'll use in the subsequent analysis to define these parameter estimation and parameter learning. Uh, and these parameters, of course, the weights of the neural network. And we will hopefully be able to show that you have nice stable performance the way you require, right? So we'll continue with our discussion in the subsequent session, and I hope to see you again soon. Thank you.